Hello everyone, welcome to Group 11's presentation on the GEO project. This presentation illustrates the engineering performance of a rigid foundation embedded in soft clay to a depth of 0.6 meters and analyzes the effect of cementation of foundation performance enhancement. For solving problems, this study starts with the constitutive module calculation of the foundation and the results are simulated in standard Civl software using the FEM, as well as including the validation of FEM results. Secondly, this study continued with the analysis of the enhancement of soft clay stiffness by cementation materials. As a summary result, higher loads will produce higher deflections and unfamiliar boundary conditions will lead to structural complexity. Also, displacement calculations prove that higher percentage ratio of displacement will show higher settlements. Construction of buildings and the geographical environment in which they are located have become increasingly complex with the development of modern society. The construction of objects on complex geographies requires a deeper understanding of the understandability of foundation and foundation reinforcement. By performing constructive module calculations, FEM simulations, and verification of the provided soil and foundation parameters, relevant conclusions are drawn regarding the influence of foundation settlement and cementation material on foundation reinforcement. The finite element method, which is also called FEM, is a popular method for numerically solving differential equations encountered in engineering and mathematical modeling. The finite element method is a general way for solving boundary value problems with multiple spatial variables. The finite element method allows a large system to be subdivided into smaller and simpler parts called finite elements to solve a problem. There are approximately 6 steps required to analyze the problem using the FEM. Firstly, a clear understanding of the defined problem is particularly in boundary conditions. Secondly, appropriate desensitization of the problem under research. Third, a constitutive module calculation of the problem under study. Fourth, establish appropriate boundary condition for the object. Fifth, the calculated data and set the boundary condition are submitted into the standard Civl software for simulation. The last, for processing and verifying the results obtained after the simulation.
Now let me talk about constitutive models for Civl. Constitutive models are assigned to enable estimation of behavior and prediction of actual complex swells reaction for applied load. Failure theories describing constitutive models identify swell failure or yielding with boundary surface, dividing the principal stress space into linear, elastic, and plastic material behavior. Ideally, a perfect swell model will be able to predict these swell behavior under all type of loading condition. An increasing number of stress relation have been formulated to model the behavior of swell. This model can be grouped into the linear elastic, non-linear elastic, variable morally, elastoplastic, and hyperplasticity. Solution in constitutive modeling have been based upon the Hooke's law of linear elasticity for describing swell behavior under working load condition, and Coulomb's law of perfect plasticity for describing swell behavior under collapse state. Generalization of Hooke's law and Coulomb's law is formulated in plasticity framework and is known as Moore-Coulomb model. However, it is well known that swell is not linearly. For finite element analysis of the foundation, the geotechnical structure is made up of concrete. It is assumed that the concrete behaves linearly elastically. The ground swell is soft clay. FEM analysis of foundation performance is on-drain situation are suggested. It is suggested that the on-drain behavior of the swell be modeled by the linear plastic perfect model. Swell is assumed to be homogeneous and uniform. However, we solve the linear problem where the material behaves linear elastic with small displacement and small strain. If it is non-linear material, then there will be a large displacement and large strain. And during evaluating the performance of the foundation, the simulation may be stopped at the settlement of 0.1 B. If it is found that the ultimate failure of load does not exist, the validation of FEM results should be performed. So we will choose linear elastic material and shallow footing for the analysis.
Description about the modeling. Description is about the modeling. That is about the foundation tool, shallow foundation we have selected for our geometrical model. So basically, the breadth is already given, B and D is already given, so we have to find WB and HB to complete our model. So size of the foundation we have found by using this formula, and depth of the foundation is HB. That is we have found by dividing the B with the 5. So basically next is the basic procedure that we have followed during preparing the FEM software, which is as when I preparing our geometry model in the strat 7. Before starting my project, I'm feeling that strat 7 is too hard, but when I follow the lectures that is provided by the Alex and the Martin, which is very helpful for me, I'll become successful to prepare a model or to complete my assessment by follow the lectures that is provided by both, which is very helpful and crucial information provided in this lecture, which is very helpful in future as well. So procedure for using the FEM software, basically we create a nodes and element, then we apply some boundary conditions, material properties, and finally the load increment is done, and basically the displacement we have realize and finally analyze the final results. So basically when I start foundation process, I'll create some nodes according to the coordinates. Then we create an element and the quadrate. The blue color that is shown, it's an element created by, and in the small dots you can see in the image, which is the subdivision of the element. Subdivision is also done very carefully. Afterwards, we also do like a clean the mesh and clean the geometry, which is very important step before assigning the boundary condition. So applying the boundary condition is second step. So it is very important to provide exact boundary condition because the structure is dependent upon these conditions as well. So go to the load and freedom case. Here you have to select the 2D plane. In the 2D plane, you have to do in the x direction and y direction. So vertical and horizontal, you have to provide the restraint and boundary condition. Then you have also provide the restraint at the F base and F shaft as well. So next is the material property. Here the modulus is given and Poisson ratio is given. You have to provide the 2D plane strain and then provide this information, and finally also select the elastic plastic module and select the mobile column. Next is the load and displacement. After that, you have to provide the load increment. Start from the lower. So firstly you have take the load in a very small amount, then you have to increase it by providing increment. So after that you can go to the solver and release the results. So basically you go to the displacement scale, and scale you have selected 0%, then 5%, then 10%. So basically I'll describe in the image, it's a 5% displacement in the first image, and in the last image you can see displacement at 20%. I'll also provide one colorful image that shows that most probably displacement occur between the F base and between the F shaft. So basically you can see in the screen here the basically displacement. So this is the critical section which create, I think so, failure. This is the graphical results of the F base. The detail is given in this section. You can see the nodes in sum and length all is given here. So basically this is for F shaft. This is the vertical. So this is also provide the detailed information. So this is the plane stress and plane strain in our foundation. So this is the exact where is the maximum and where is the minimum. You can see it's provided here. Next is the shallow foundation. So complete model of my foundation is here. The basically I we have to realize that the basically failure is occur here between the F base and F shaft. So this is the main cause of the failure. Good, thank you.
In conclusion, we analyze all the parameters in shallow foundation to obtain results about stress, strain, displacement, boundary condition, and material properties. Qualitative and quantitative analysis has been done after getting the results on StrandSAM software to provide accurate results on shallow foundation. Higher the load will produce high deflection, as we can see in the diagrams. That means the load has significant effect on the foundations. Boundary conditions are important to execute for the stable shallow foundation. Unfamiliarity with the boundary condition can lead to collision of structure. Calculation of displacements prove that higher displacement scale will show high settlement. If you have any question, you can ask. Thank you.